Welcome, dear learners. Welcome to the GATE training course on mechanics of materials. This is lecture 1, lecture on stress, strain, and elastic constants. I am S. Pradesh Murthy, Assistant Professor, Government College of Technology, Coimbatore. The topics for discussion for this lecture are loads, stresses and types, strain and types, the Poisson ratio, elastic constants, relation between elastic constants, some example problems, and finally the conclusion. Now, loads. So definition of load is any force acting on a body of consideration. We are considering a body and we are going to study about that body, and if any force is acting on that body, we call it as a load. The types of loading, depending on concentration of load on area of action, the loads are classified as three. One is point load, uniformly distributed load, and uniformly varying load. In a point load, the whole load acts over a very small area. So the area of application is very small. So we consider it to be acting on a single point. So look at this diagram. So assume this to be a body over which a load is acting. We assume that to be acting over a single point. So that type of loading we call it as a point load. And uniformly distributed load, this load acts in such a way that the magnitude per unit length is constant. So assume this is a length of action of the load. So over this length, the load is acting, and the load acts uniformly. So assume I'm giving a magnitude of 10 kilonewton per meter. That is, the 10 kilonewton load will be spreaded over a length of 1 meter uniformly. That is, when I start from one end to a distance of 1 meter, the total load acting will be 10 meters. So per unit length of acting of load, the magnitude will be 10 kilonewton, right? So the rate of loading is constant. So now uniformly varying load. Here the load acts in such a way that the magnitude per unit length or area of specification increases or decreases linearly. Look at this diagram. When I am considering from the right towards the left, the magnitude of the load increases in a linear manner. Assume at the right end, if the load is 5 kilonewton and I am giving a load value of 10 kilonewton per meter, and if the length of application of load, this length is 1 meter, right? So this is 5 kilonewton and the length is 1 meter and giving a rate of loading of 10 kilonewton per meter. So when I am crossing a distance of 1 meter, another 10 kilonewton of load will get added. So here it is 5 and here it will be 15 kilonewton, right? So this type of loading we call it as uniformly varying load. Now, depending upon variation in magnitude of loading, we classify it as steady or dead load, varying or live load, suddenly applied load or shock load, and impact load. Steady or dead load. So magnitude of load does not varies with time. Example, on a table I am keeping what you can say a table weight. So depending on time, the load will not vary, right? So that type of loading is called as steady or dead load. Varying or live load. So the magnitude of load varies over time. So here the loading either varies from 0 to a maximum and then 0 again maximum to 0. So it may be varying like that, or it can vary from a minimum value to a maximum value. Say it may vary from 5 kilonewton to 10 kilonewton again to 5 to 10. So it may vary like that, or otherwise it can vary like this. Say from positive 5 kilonewton to minus 5 kilonewton, again positive 5 kilonewton to minus 5 kilonewton, like that it goes on. Normally we say positive loading as tensile loading and negative loading as compressive loading. Okay. So now then the suddenly applied load or shock load. The whole load is applied at a very short interval of time. So assume the same case of a table weight. If I am keeping it very slowly, we can say it is a gradually applied load. And if I'm suddenly keeping it, right, I am keeping it very close towards the table or a table and I'm suddenly placing it, right? Then that type of loading is called as a shock load and impact load. So the load is associated with an initial velocity. So assume a bat hitting a ball. So the bat will be coming with a velocity, and in a very very short interval of time the force is applied on the ball and the ball travels with another velocity, right? So whether the ball travels with a velocity or not, that's not the matter. The matter of the fact is the force applying medium. It comes with an initial velocity and applies the force, right? So that type of loading we call it as impact loading. Now stress and strain. The internal resistive force developed per unit area of a body is called a stress. So whenever we apply an external loading, the body reacts to it. So it develops a resistive force. So that resistive force developed per unit area, we call it as a stress. So when it is under equilibrium, the external force will be equal to the internal resistance. Hence, the stress sigma is equal to P by A, where P is the force in Newton and A is the resisting area of the body in meter square. So the unit of stress is Newton per meter square. Types of stresses. So depending on the mode how the force are acting, we classify it into two. One is the normal stress. So stress developed due to the force acting normal to the resisting area. So here the external force acts normal to the resisting area. So uh, we classify normal stress into two: tensile stress and compressive stress. In a tensile stress, the external force tends to expand the body, whereas in a compressive stress, the external force tends to shorten the body. So let's look into it. Look at the diagram. Look at this diagram. Assume a body, okay, a rectangular block, where the red arrows indicate the external load. So this hatched portion indicates the area over which this loading is acting. So this force acts normally to this region. So I have made a cross section along A plane. So this red color, it indicates the external force applied, and the internal resistance to counteract the external forces is shown in the green color. So these forces are developed internally, the internal resistance. So these forces per unit area is called as stress, right? So in this case, it is compressive stress since the loading is compressive. Now look at what happens at the molecular level. Assume these circles to be the molecules, right? There will be some intermolecular distance, right? These compressive forces try to reduce the intermolecular distance, right? So the material offers a resistance to maintain the same intermolecular distance. So that resistance is represented by this green arrows, right? Here this load tries to pull it towards the right, and this green arrow, it tends to stop it from pulling inside, right? So this is what happens at the molecular level. So similarly, in case of a tensile loading, here the opposite happens. The external loading represented by the red arrows tries to pull or stretch the material, right? Again, I have made a cross section along the AAA plane, and this green arrows are the internal resistance developed to counteract the external forces. So these internal resistance developed per unit area, we call it as stress, right? Remember, when it is in equilibrium, the external forces will be equal to the internal resistance. So simply we call it as force per unit area. So now look into the molecular level. So these tensile forces try to expand or increase the intermolecular distance. So the internal resistance tries to maintain the original intermolecular distance, right? So this internal resistance per unit area, we call it as tensile stress. Now, the second type of stresses, tangential stress or shear stress. So external force acts tangentially to the resisting area. Previously, it acts normally. Now, this forces acts tangentially to the resisting area. So again, this tangential stress or shear stress is classified into two types of stress. One is direct shear and the other one is torsional shear. So in the direct shear, two equal and opposite forces acts tangentially across the cross section. Across a cross section, this tangential forces acts equally and in opposite direction, right? So it is represented by the letter tau, which is equal to P by A in Newton per meter square, where P is the tangential force in Newton and A is a resisting area of the body in meter square. Now, the second type of shear, it is torsional shear. Two opposite torques acts on a cross section. Okay, either it may be two external torques or it may be an external torque and a resisting torque due to fixed end or whatever it may be, right? So this torsional shear stress, the formula, it is again represented by tau, which is equal to T into R divided by J, and again the unit is same in Newton per meter square. So where T is the torque in Newton meter and R is the distance from neutral axis in meter, J is the polar moment of inertia in meter power 4. We shall discuss this later. We call this as the torque equation. We can discuss it in detail in the later lectures. Right now, we can move on to the next. We can have a diagram showing the direct shear and torsional shear. See here, let us assume this to be a rectangular block, and to this cross-sectional area, the shear load or shear forces act tangentially, right? Previously, it was normal like this, as shown by cursor, as shown by my cursor movement. Now it is tangential, right? From here and here. As mentioned earlier, it is two external forces equal and opposite in direction, right? Now I have made a cross section again along AAA plane, and look at here. To the leftward shear forces, just to the left of the plane AAA, an upward force is developed, and a very small distance to the right of the plane AAA to counteract the rightward upward forces, external shear forces, a downward internal resistance is developed, right? So come to the molecular level. So across a molecular layer of arrangement, on one side the forces are acting downwards and on the other side the forces are acting upwards. So to counteract the forces acting downwards at the left end, upward forces produced, and again to counteract the upward forces at the right end, downward forces produced. So this is shears, right? So shear stress. So this internal resistance developed per unit area, we call it as shear stress. So the only difference is in normal stresses, the force acts normally, and in shear stresses, the force acts tangentially. Now coming to the torsional shear. So assume we have a shaft and one end of it is fixed, and this red color arrows represent the torque applied. Instead of external loading, now we call it as external torque, right? So now whenever a clockwise torque is developed, a counterclockwise torque is developed, or internal resistance is developed inside the material to counteract it, right? So assume a molecule at the point A, right? So now due to the application of the torque marked in the red color arrow, so look at the image here. Previously it was at A, and after deformation it has moved to a new point A dash, right? So it is stressed. Look at the lines from here. The green ones are the one which was initially there, and after loading it has shifted to a line, red line. So right, every material or every atom along the green line has now moved towards a new location, that is along the red line, right? Now come to the shear stress at molecular level. Look at the center point O of the cross section of this circular shaft. When moving from O towards A, let's have different molecules in different layers, right? When we are moving from radially outwards from O to A, now the A point has moved from A to A dash, right? Similarly, the adjacent layers of molecules present along the plane OA has now shifted to a plane OA. Now visibly we can see the difference. From A it has moved to A dash, and at O there is no change at all, and when we are moving from A dash towards O, the distance of movement of each and every molecule is decreasing, and finally at O there is no movement. Let me clear it once again. At the point A it has moved to A dash, so the distance is larger. When you are coming downwards, the distance of the particle which was previously there, and after loading it has moved to a red zone. So distance of movement keeps on decreasing, while when it reaches O, the movement is nil. So which mean the molecule which are at the outer end or at the periphery moves over a longer distance, or which are distorted more than the one which are closer to the center, right? So at the center, by theory there is no movement at all. So at the center there is no stress produced at all, or there is no resistance produced at all, whereas at the outer periphery, due to the larger displacement, it has to give a larger resistance. So the stress distribution, look at the stress distribution. At the center, the stress is nil, and at the external periphery, the stress is more. So the torsional shear, the stress varies linearly from 0 to a maximum at the end. The point where the stress is 0, we call it as the neutral point. The axis connecting the left end to the right end of the shaft, where through which there is no stress at all, that is called as neutral axis. We can see it in detail in the torsional topic. Now still, we need the basics for torsion shear. So keep one thing in mind, direct shear and torsional shear both are one and the same, but in direct shear the stress is even, but in torsion shear from neutral axis to the outer periphery the shear increases in a linear fashion. So keep this in mind. Now we can move on to the strain. As I sorry, as I said before, whenever an element is stressed, it will tend to elongate the material or shorten the distance of the material. So let's see that. So the ratio of change in dimension of the material after loading to the original dimension before loading. So that we call it as a strain. So again, this strain is classified into two: longitudinal strain and lateral strain. Let's say, what is a longitudinal strain? Change in dimension along the direction of load by original dimension. So that we call it as a longitudinal strain. See here, come to this diagram in the tensile loading portion, right? So in this diagram, L is the original length of the material and we are applying a tensile load of P at its ends, and due to that the material has now increased and the final length is L plus dl. Whenever the length increases, the width or breadth of the material decreases, right? Previously the breadth was B and now it has reduced by a distance delta dB. That is, so the now the final breadth is B minus dB, right? So now along the linear direction or along the longitudinal direction or the direction of loading, the length has increased by dl, and in the lateral direction the width has reduced by dB. So the dl by L, that is change in length by the original length. So this is the direction of along the direction of loading. We call it as longitudinal strain. So strain is normally denoted by the letter E. So we write it as E longitudinal is equal to dl by L. The same is in the case of a compressive loading. So assume we have a material of length L loaded by a compressive load P of breadth B, right? After loading, the length has decreased to L minus dl, and whenever the length is decreased, so the breadth increases. So now the breadth increases to B plus dB. So this change in length, so dl was the change in length, so dl by L, so we call it as E longitudinal. So whether it is tensile loading or compressive loading, so it is one and the same. E longitudinal is dl by L. And now the lateral strain, change in dimension in a perpendicular direction of load by original dimension. We call it as lateral strain. So we are giving load in the length direction along the direction of length, but there is change in breadth, right? So in the lateral direction there is some change in dimension. So change in dimension along the lateral direction is dB, whether it is compressive or tensile loading. So the change in breadth is dB. So dB by B, we call it as the lateral strain, right? So in case of tensile loading, in E longitudinal, the length will dl will be positive. That is, it is increase in length. Whereas compressive loading, the dl will be negative. But we take the magnitude only. So it is dl by L. So it has no unit since it is length by length. And again here change in breadth by breadth. So if it is tensile loading, dB will be negative. If it is compressive loading, dB will be positive. Now Poisson's ratio. So it is a ratio of lateral strain to the longitudinal strain. So we have a factor connecting the lateral strain and the longitudinal strain. So longitudinal strain is a strain along the direction of loading. So lateral strain is the strain along a direction perpendicular to the direction of loading. Right. So we have a factor now connecting the lateral strain and the longitudinal strain. Right. So it is a ratio of lateral strain to the longitudinal strain. Now, Poisson's ratio, since it is again the ratio between strain and strain, it is a unitless number. Unitless number which indicates the degree of lateral deformation for a longitudinal load. So if the Poisson's ratio is more, it indicates that whenever you apply a a load along one direction, the deformation in a direction 90 degree to the load will be more, right? So it is denoted by the letter mu r 1 by m. So Poisson's ratio of some of the common materials is mentioned below. Material granite, the value is between zero point 0.2 to 0.3, and cast iron, the value is 0.22 to 0.3. Steel, high carbon steel, the value is 0.295. Steel, mild steel, it is 0.3. Aluminum, it is 0.334. Copper, it is 0.355. Rubber, it is 0.48 to 0.5. It is nearly equal to 0.5, right? So here from this table, I want to mention one thing. You know, granite, it is a stone, right? So it is rigid, nearly rigid. So when you give a loading, right, the value is nearly 0.2 on the lower side, right? So it will not deform laterally that much. So a material which are, what we can say, stronger or which are less ductile, it has lower Poisson's ratio, right? It is a normal case. There will be exceptions also, right? So the value starts around 0.2. When you move towards the right of the table, see from 0.2 it has moved to 0.2 to 0.3, right? And it is much more ductile than granite, right? So here the value has increased from 0.2 to 0.3, right? Still, cast iron is much more brittler than other types of iron, right? So now steel, so it is little bit more ductile than cast iron, right? So it has a value 0.295, which is higher than the lowest value of cast iron. Mild steel, it has again a higher value. Aluminum, it is again ductile than steel, so it has a higher value around 0.334. And copper, it is much more ductile, so it has a value 0.355. And rubber, it has a value 0.48 to zero point 0.5. You know, rubber, it is one of the most ductile material, right? We can say ductile, or we can say it is an elastic material. It is more flexible, so it has a higher value. So what you want to remember here is the value of most common engineering materials will be around 0.22. Say here it is 0.355, right? So around 0.22 to 0.4, most of the um, engineering materials, the value of Poisson's ratio will of most of the engineering materials will lie in this range, 0.2 to 0.4, right? Not more than that, right? So here rubber, it is around 0.5. Okay. Now shear strain, right? We have till now we have seen about normal strain and Poisson's ratio. Now it is shear strain. A ratio of relative displacement of any layer to its perpendicular distance from the fixed layer. Right, assume in this diagram, this is one layer, right? This plane, and this is another plane, right? So due to this loading, assume this is grounded, this portion is grounded. So due to the shear load, this has shifted laterally. to this much height, that is dh, right? So there is angular deformation. So along the length, when you are moving along the length, there is movement along height, or there is deformation along height. When you are moving along length, when you are moving along the length, there is deformation along the height. So this we call it as shear strain. So shear strain is represented by the letter gamma. So it is dH by L. So dH is this deformation, deformation in height, and L is the original length of the object. So dH is, when you consider this to be a triangle, so dH, this is the opposite side, and L is the adjacent side for this angle phi, right? So we can call it as tan phi. So shear strain, either you can represent it as gamma, or we can say it as tan phi. Now come to elastic constants. So normally we have three elastic constants. So we have one constant before, we call it as Poisson's ratio. It connects lateral strain and linear strain. Now we want to connect between stress and strain. So we have three constants. So let's see one by one. Young's modulus or elastic modulus E. So it is a ratio of normal stress to the normal strain within the elastic limit. Remember, within the elastic limit. We will see that later in the stress strain diagram, but now remember the word elastic limit. So elastic limit, there is a limit for loading up to which the material upon the release of load comes back to the original position or original dimension. We call it as the elastic limit. So within the elastic limit, so once again keep this in mind, within the elastic limit, right? So it is the ratio of normal stress to the normal strain within the elastic limit. So it is an indicator of strength of the material in tension or compression, right? So whenever we have a higher elastic constant, that is higher Young's modulus, it means the material is stronger, right? That is, it is stronger in tension or compression. So it is used to design in the design of beams, columns, etc. So while designing beams, columns, trusses, in all these things we use the modulus E. So depending upon the Young's modulus E, we classify materials as a stronger material or a weaker material, right? So Young's modulus E is equal to stress by strain, where stress is load by area and strain is change in length by original length. So we can say Young's modulus is PL by A into delta L. The unit is in Newton per meter square. And now the rigidity modulus or shear modulus, it is normally represented by the letter G. We can also have the letter as C and N also as its representation, right? Somewhere in some places we use the letter C, in some other places we use the letter N. Okay, now let's use the letter G for representing rigidity modulus or shear modulus. So rigidity modulus, it is the ratio of shear stress to the shear strain within the elastic limit, right? So it is a ratio of shear stress to shear strain. It is an indicator of strength of the material against twisting or shearing. So it is the indicator of strength of the material against twisting or shearing. So whether the material is easily twistable or easily shearable or not. So this is represented by rigidity modulus. Now the third one is, it is used in the design of shafts, springs, crankshaft, etc. So for designing shafts, springs, crankshaft, etc., we use rigidity modulus. So rigidity modulus is represented by the letter G, which is equal to tau by gamma, where tau is shear stress by shear strain, right? Now bulk modulus K. It is the ratio of volumetric stress to the volumetric strain within the elastic limit. So volumetric stress is the stress acting over the entire volume. That is a stress equal in all direction, and it tries to increase the volume or decrease the volume. Normally an external pressure will be the volumetric stress. So now it is an indicator of incompressibility of the material. So if the material has more bulk modulus, its volume will not decrease. If its volume is not decreasing, which means it is incompressible, right? So this bulk modulus is used in the design of hydraulic power systems. So in hydraulic power system, we'll be using some hydraulic oils as the power transmitting element. So there, if it is compressible, it is very difficult to positioning a system, right? So for positioning and everything, so that fluid should have some rigidity, sorry, some bulk modulus, right? So here I have mentioned it as rigidity modulus. It is wrong. Here it is bulk modulus. Bulk modulus K is equal to P by EV in Newton per meter square. Now the relation between elastic constants. So first one is the relation between Young's modulus and rigidity modulus. So here the relation is capital E is equal to 2G into 1 plus 1 by M, where 1 by M is the Poisson's ratio, right? We have a detailed derivation for relating these two, but at this point of time, the derivation is not needed. So keep these three relations in mind. E is equal to 2G into 1 plus 1 by M. And the relation between Young's modulus and bulk modulus is E is equal to 3K into 1 minus 2 by M. And the relation between Young's modulus, rigidity modulus and bulk modulus is E is equal to 9 kg by 3K plus G. Right? So I hope I have covered the portions in relation with load, stress, strain and elastic constants. And now we can have some simple problems. Right. Find the strain of a brass rod of length 250 mm which is subjected to a tensile load of 50 kN when the extension of rod is equal to 0.3 mm. Right. So here what is given in the question is the length is given, the external load is given, and the change in length is given. So we are asked to find the strain. So the strain is change in length by original length, right? So the change in length was 0.3, right? And the length was 250, right? Both are in mm. So change in length by original length, the value is 0.0012. So that value, that is B, is going to be your answer. So here this 50 kilonewton has no use in solving this problem, right? So that value is given to confuse you, right? Now how can I make this problem much more complicated? So now instead of in the same problem, instead of asking for the strain, if I can ask the lateral strain, how it will be? See, the same problem, I am asking for lateral strain. For finding the lateral strain, I am giving one more value, the Poisson's ratio, right? So as before, you have to find the strain and then use this relation. Poisson's ratio is equal to lateral strain by longitudinal strain, right? From there, I can get the relation lateral strain is equal to longitudinal strain into Poisson's ratio. So from that, I can get the answer, right? So look at these answers, right? So in the answer option, I have the correct answer as well as see here 0.0012, which is the linear strain. So linear strain is also given as the answer, right? So whenever you solve it, initially you will be getting this value. So someone has a tendency to, so if you get the same value in any one of the option, they will take it because they assume whenever we are solving it, some value is right in the option, that may be the right answer, right? So to confuse you, this value will also be given, right? The answer, right answer is given. And instead of multiplying it, if I am dividing it, right? If I am dividing it, I may be getting this value, right? 0.004. If I am dividing it, maybe, right? So to confuse you, the values will be somewhere around there, right? But you should be thorough with the correct formula, then you will not get confused. Then another. Find the elongation of a steel rod of 100 length when it is subjected to a tensile strain of 0.005. So here the strain value is given and you are asked to find the elongation, right? So strain, so change in length by original length was strain. So again, you can easily find the value, right? Strain is given and length of the rod is given and you can find the change in length. Now, which law is also called as the elasticity law? So it's Hooke's law. So I will explain it later. So in the stress strain diagram. So remember, Hooke's law is the law which says stress by strain is constant within the elastic limit. Next question. The Young's modulus of elasticity of a material is 2.5 times its modulus of rigidity. Then what will be its Poisson's ratio? So now here we have a problem with the relation between elastic constants. The relation between E and G is E is equal to G into 1 plus mu, right? So here it is given E is equal to 2.5 times, right, G. So E is equal to 2.5 G. Substitute it in this formula and you can get the value of mu, right? Either way I can ask the question. Either I can give the value of mu and I can ask you to find G, or now indirectly I am giving G and I am asking you to find mu, right? Next. Which of the following is true if the value of Poisson's ratio is 0? Right? If the Poisson's ratio is 0, the material is rigid, the material is perfectly plastic, the longitudinal strain in the material is infinite, right? There is no longitudinal strain in the material, right? So come back to the relation between E and G, right? If Poisson's ratio is 0, right? G is equal to 2E, sorry, G is equal to E by 2 into 1 plus mu. So I have altered this equation in this manner, right? When I am substituting this value as 0, so for every material, there will be a positive value of mu, right? But if this value is 0, assuming it to be a 0, then G will be maximum, right? If mu is 0, then G will be the maximum. So if G is maximum, G indicates the material is rigid, right? It is rigidity modulus. If G is more, then the material is rigid. So it indicates the material is rigid. So the answer is the material is rigid. Next question. What will be the value of Poisson's ratio if the Young's modulus E is equal to the bulk modulus K? So the same relation. So E is equal to K. Just substitute in this relation and find. So you can get mu is equal to 1 by 3, right? And what will be the stress developed in a steel bar of 20 square cross section when it is subjected to a tensile load of 60 kilonewton? So stress is asked. So we know the relation between for stress. Stress is equal to load by area. The load value is given. and the area is indirectly given as a square rod of 20 mm cross section, right? So we can calculate the load by area. Area, the dimension is given in mm and I have got converted it into meter, so I can get the value. Next, what will be the strain developed in a steel bar of 20 mm square cross section when it is subjected to a tensile load of 60 kilonewton when E is equal to 2 into 10 power 5 Newton per mm square? The same thing here, Young's modulus is given, the same problem. I want to, I have asked you to find the value of strain. So the relation between stress and strain is Young's modulus. So Young's modulus is equal to stress by strain. So E is equal to, so in the problem in extra I have given the value of Young's modulus, so you can easily find the value of strain, right? With this I conclude this lecture. Thank you.